Hello students, let's talk about depth first search or DFS today. Alright, so we were talking about graph traversal techniques. We will start right off where we left for BFS. As you already know, traversal means visiting all the nodes of a graph. Depth first search or DFS is a graph traversal technique like BFS as well, but with a different approach. So let's think you are designing a Google Map application. You have multiple cities. Cities are connected through roads and each road has a toll booth in it. For BFS, we calculated how many toll booths we need to pay. Now he wants to know the path to reach his destination. In order to provide him a solution, you need to design an algorithm. Obviously, BFS is not the best solution here because our goal is to going to our destination first instead of traversing all the nodes in a level. That's where DFS comes to the rescue. Have a look at this figure. We want to go to E from S. We need to find a path to reach there. So how do we approach it? We can start from the initial vertex S, then recursively visit each adjacent vertex. Strategy is to reach deeper into graph, unlike BFS which fans out. Let's see how it works with an example for this graph. As you can see, we started from S, then we go to A, then B, then D, and then F, then E. We could go to C, but if we go to C, we would not have any place to go, so we would have come back to A. So, as you can see, we have found a path which starts from S, then we go to A, then we go to B, then D, then F, and then E. There could be other paths like S to A, then directly to D, then F, then E. So we have multiple paths, but this is a path we found. Of course, we would like to find the optimal path if we had some values on it, but we would explore different algorithms for that. So let's look at DFS pseudocode now and how it works. So let's start with the top. We have DFS function which has G as parameter. G stands for graph, and graph consists of a vertex and edge. Now the first task is to initialize all the items we have. So to do that, what we did is we call a for loop. So we wrote a for each vertex U belongs to our graph G. So any vertex U that belongs to our graph, we color U to white. So we color all the vertexes of our graph to white. Our next task is to go to pi U array. So this array is for storing the value of predecessors. So for now, just say we have an array called pi, and we initialized all the item of pi with nil. Then we go to time, and time at the beginning is 0. So with time, we would like to write when did we got our vertexes discovered. So let's start with our algorithm. So to start our algorithm, we call another for loop outside this for loop, not in this for loop. It's outside this for loop. So this for loop says for each vertex U belongs to B, do color white, then DFS visit U. So that means if we have a vertex which is colored white, then we start DFS visit function. So DFS visit function will actually implement our DFS pseudocode. So what do we have in DFS visit? We have our graph and U, the source vertex in here. So our source vertex now would be colored as gray because we have already discovered it. So the time would be added as 1 because whatever the time was previously, we just discovered it, so we add 1 to it. Then we have a discovery time of U, and the discovery time of u is assigned the time, so we can have the time of discovery for this vertex as u, du. Now we open a for loop. For each vertex belongs to v that is adjacent to u. So any vertex that is adjacent to our source vertex u, we go to that vertex and see if the color is white. If the color is white, then we assign the value of pi v predecessor to u, because v has a predecessor of u, and then we call DFS visit v again. So we go, what it does is we go to an adjacent vertex, and from that adjacent vertex we call this recursively again, so that we go into that vertex in deeper manner. And then what we did is, as we have finished working with u, we have colored it black, and as the color is black for u, that means we have finished working with it. So the time of finishing, which is depicted by fu, the time is assigned to it, time plus 1. All right. Let's see with a simulation that would make it more clearer. So as you can see, we have found our source u. So it is labeled 1 because it is the time of discovery, and we have colored it gray. Then we have gone to v, the adjacent vertex of u, and we have labeled it 2. So the discovery time of v is 2. You can see we did not go to x, because for our algorithm we just go one vertex which is adjacent to it, and then dig deeper to it, and once we have finished we come back to it again. So we will not go to all of the adjacent vertex at once. We will not fan out as we have done in DFS. So we have gone to v from u and label it 2. Then we have gone to y and labeled it 3. From y we have our adjacent vertex x, which is labeled as 4 now. Now from vertex x we don't have any path to go, which is not discovered yet. There are all the adjacent vertex to this x is already discovered, and they are already gray. So we cannot go any other vertex from it. So we will have to go back. So the work of x is finished. So the finishing time of x will be 5, and we'll color it black. So we have colored it black, and then we go back to our y and label it 6 as the finishing time. Then we will go back to v and label it 7 as finishing time, and then we will go back to u again and we will label it 8. Alright, so we have got this u, v, y and x, this path and the starting and finishing time of it. Now for our system or pseudocode, our graph has 2 more vertices which is still white. So we have to discover them as well. So with our for loop, we start to look for any vertex that is colored white. So we have found with this for loop that our vertex w is still white. So we start from here again. So we label it 9, and then we go back to its adjacent vertex, which is z, and label it 10. Then we have to obviously we have to come back. So we will label it 11 and color it black, and then we'll go back to w again and label it 12. Alright, so as you can see, we had the graph below where we got our final result after implementing DFS this graph. Dotted line means we did not choose this path, and the number on top means whenever we discovered the vertex and when we finished working on it. So what can we say from our results? From our results, we actually got rid of the cycle we had on the graph. So we made 2 trees out of our graph using DFS. Though there is no cycle now, it is ensured that we have path to visit all the vertices. Let's see with the image. So we don't have a circle in here. We had cycles in here. This was a cycle in our graph, so we got rid of the cycle, but it is still ensured that we can go from here to here, here, and here. There is a path to visit all the vertices, right? So we got rid of our cycle, and we still got path to visit all the or traverse all the path, all the vertices of our graph. Also, we could find separate trees in a forest. As you can see in this image, here we actually did have two graphs inside one graph, and they were connected, right? So what is a forest? A forest is an undirected graph. All of those whose connected components are trees. So in a forest there are connected components, those are called trees. In other words, the graph consists of disjoint unit of trees. So inside our forest we'll have multiple trees, and using DFS we can find our separate trees, right? We got our separate tree, this, and this was another separate tree, and this is as a whole is a forest. So from our graph we got all the separate trees using DFS. And how do we find it? We go back to our source and label it 8, and then we found a new source, label it 9. So if we can just get whenever we start a new source, that means it is a tree, starting of a tree. So DFS help us to find this tree. DFS can be implemented using stack data structure. We'll find more about them in our labs. So what are the questions we can answer using DFS? These are the questions we can answer using DFS. How to detect a cycle in a graph, how to compute the connected components. Like in DFS, start a new tree. Each tree representing a connected components. I already talked about it. Ignore with the line 7. If you find our old slides, you'll find that we have all the pseudocode lines numbered. So that this 7 is that. Of what we use, discovery and finish time. What are the different types of non-tree edges in BFS or DFS tree of an undirected graph? What about the directed graph? How to use the DFS to topologically sort a directed acyclic graph or DAG. So we'll later know more about topological sort and directed acyclic graph. This question will be more clear by then. Alright, so what is the complexity for our DFS? As you can see, DFS runtime complexity is same as BFS, which is big O, B plus A. Alright students, so that's it for our DFS. Thank you for watching. Have a great day. Bye.